Hi everyone, and welcome to MathSux. This video is going to help you pass the Geometry Common Core Regents. So we're doing this one question at a time. Here is question 17. On the set of axes below, pentagon ABCD is congruent to ABCDE double prime. So we have this picture here. We see that we started with this pentagon in quadrant 1, and then we did some stuff to it. We're not sure yet what we did, and we end up with this pentagon flipped and rotated in quadrant 3. So then it asks us which describes a sequence of rigid motions that maps ABCD onto ABCDE double prime. So let's just do the each example. Let's just do each choice until we get the right answer and see how it goes. So let's look at number 1. So rotation of 90 degrees counterclockwise. So counterclockwise, remember, means we're going the opposite the way of the clock goes. So we know that we're going to the left. So we're going to be going this way. So if we take our point A, for example, so we start here, 1, 2, 1, 2. So we have point A at 2, 2. And we want to go 90 degrees to the left. So 90 degrees to the left would give us A prime, negative 2, 2. So just a little reminder of what the rule is for counterclockwise to the left is x, y, and then, so we start with x, y, and then it becomes negative y, x. So that's all we did here. We have 2's on both sides, so we just really needed to negate this value right here. So let's just put that on our paper and map that on our paper and see what happens. So we have negative 2 up 2, okay, at the origin. So that was just the first step of choice 1. Followed by a reflection over the x-axis. So if we were to reflect this point over the x-axis, we'd end up over here. So this is a point, E double prime, but remember this is A prime that we just moved. So based on this is not our answer, number 1. So let's try number 2. A rotation of 90 degrees counterclockwise. So we already have that. We still have our A prime there. About the origin, followed by a translation down 7 units. So a translation down just means we're going to move down 7 units. So that means we're going to bring this point down. 1, 2, 3, 4, 5, 6, 7. And notice we end up where we want to be, A double prime. So we know that this is our answer. So we just translated one point, but if we were to translate all the points, we would end up with our pentagon, ABCDE double prime. Question 18. On the set of axes below rhombus ABCD, his vertices whose coordinates are A, 1, 2, B, 4, 6, C, 7, 2, and D, 4, negative 2. What is the area of rhombus ABCD? Let's split this into triangles and see if we can figure it out. So if you look here, we see that if we just focus on this triangle, we could see that this forms a right triangle, right? We can see that the base of this, 1, 2, 3, is 3 units. And then the height, 1, 2, 3, 4, is 4 units. So this happens to be a Pythagorean triple, where this third length, the hypotenuse, is 5. So if you want to do that the long way, we would just do the Pythagorean theorem, 3 squared plus 4 squared equals c squared, which will give us 9 plus 16, which gives us 25. And when you take the square root of both sides, you'll see 5 is equal to c, the hypotenuse. So we still don't know the area of the rhombus yet, but we are able to figure out the area of this triangle right here. So area of a triangle is 1/2 AB, right? Base times height. So if we do 1/2 base times height, 3 times 4, this will just give us 6, right? 12 times 1/2 is 6. So this is still not our answer because we have this entire rhombus that we want to know the area of. Notice that there are 4 of these triangles altogether, right? We have one over here, we have one over here, 3, 4. So there's 4 triangles with this area. So we're just going to multiply this area by 4, which will give us 24. So the answer here is 24 to 19. which figure below can have a triangle as a two-dimensional cross-section? So a cross-section, all that means is like you're taking a three-dimensional shape and you're cutting it in half, and you're kind of seeing what shape that forms. So if we look at a cone, it looks like this, right? So if we were to slice this right down the middle, if you were to take one slice of this cone and kind of take it apart, it would form a triangle, right? Or if you took it from the bottom, from down here, it would form a circle. So that's what we're doing with cross sections. And they want to know specifically which of these shapes can have a triangle cross section. So right away we could see that a cone does have a triangle cross section. So let's just mark it, a cone, yes, but let's keep going because there's other potential choices. So how about a cylinder? So a cylinder looks like this. So if we were to cut it in half this way, we would get a rectangle, and if we were to cut it around this way, we would get a circle. So no. So we want a triangle, so no to number 2. Number 3, a cube. So a cube is tricky because it can be cut so many different ways. So of course we can cut it the typical way, this way, which will give us a square, or we could cut it this way, which will give us another square. But it's tricky because you might not think of cutting it on the diagonal, which would be a triangle. So if we were to slice this piece right here, so let me show it another way. So if we were to slice this piece right here, notice that this would become a triangle. So yes, a cube. And number 4, a square pyramid. So I think right away we can see that if we were to cut along here, this would form a triangle. So yes, so our answer must include cone, cube, and square pyramid, which is 1, 3, and 4. Choice 4. And that's our answer.
Need more practice? Check out MathSux.org for more questions. Link below. Also, don't forget to subscribe. Happy calculating!